Yeah. Now, how are we, class? We are very, very fine. Yeah. Now, today, we are back. And I request for maximum attention. Now we want to proceed through, because we started and so far we have covered 2 topics of Senior 2. Now we are going to the 3rd topic of Senior 2. We covered topic 1, and that was topic 1. That was acids, bases, and indicators Then topic 2 took us to salts. Then today we are introducing in topic 3. See, now it happened that each topic here was a bit long because there are many concepts. It took beyond 2 hours per topic. It's more than 2 hours. Now today we are going to look at a new topic called periodic table and the atomic structure. For today. Now I request that we pay maximum attention, and I've brought to you 2 books. Chirabo, bring one here. Today 2 of them. I've brought for you 2 books. That is research books. That is new certificate chemistry by 6th edition by Holderness and Lambert. New certificate chemistry 6th edition by Holderness and Lambert. It's a blue book. So we are going to use the periodic table that was placed behind here. I brought it for the periodic table, and consequently you will visit the notes on the periodic table to make more studies. Yeah. Now the periodic table is just behind here. Is what I wanted us to really look at how it is really arranged. Yeah, how it is really arranged. Yeah. Now this is the periodic table from this book called the Holderness and Lambert. Then I want to bring you another one here. This is a full course, Form 1, Form 4, you can consult in it. Then I bring you another one here called the new chemistry students book for Senior 1 and Senior 2. And it's written by Arthur Atkinson, Richard Walugere, and Titus Tayewa. We are going to basically go to that part of periodic table which is on page 104. page 100, 104. Yeah, it's on page 105. That periodic table will be very, very helpful to us in breaking down the periodic table. To us to be very, very important. Yeah, we shall use it when you are doing your research work. Consult from here, plus the new certificate chemistry, plus internet. That means you Google internet. Now let us start. The topic is long. The topic is long, and being long, we need to keep time. Now our topic here is periodic table and atomic structure. See the atomic structure. See. Now in that topic we are going to split it into subtopics so that we can get a smooth way. That means we shall isolate the periodic table itself alone, then atom alone. That means we can have periodic table alone, and then the periodic table we shall break down meaning of that periodic table, meaning of the periodic table. See? Then we shall also we shall also look at the structure of the periodic table, structure of modern, because the first periodic table was improved and called modern periodic table. Then we shall finally see what we call chemical families. See, then it will throw us on atomic structure. Then we look at an atom. See, then we see fundamental particles of an atom. Fundamental particles of an atom. See. Then we shall look at symbol of an atom. Symbol of an atom. See, when we look at the symbol, it will take us to what now we call the isotopes and the isotopy. Then it takes us to electronic configuration, electronic structure, stroke configuration. Then we look at stability of an atom and ion formation. And ion formation. Okay. So, there are so many here. Then we shall also break down and visit what we call the atom electronic structure and the periodic table. How can we relate electronic structure and periodic table? See, there are so many. So Then we shall look at valency, the valency of elements, yeah, which will finally throw us onto what we call the chemical formula, chemical or formulae. See, chemical formulae and equations. Yeah, that's quite a lot. See, it's quite a lot. Yeah. That means it is costly. You must be attentive, follow system, because each part takes us to another part, interconnected all through. See? Yeah. Let us start with the periodic table and its meaning. See that? Yeah. Periodic, yeah, table. Now we want to see what does that one mean. Meaning. Under that, I'll first ask you one thing. At home, how is your cupboard arranged? Let's take the cupboard having household utensils, plates. What? How have you arranged that cupboard? Spoons, plates, glass things. Have you thrown them anyhow, or there is some form of arrangement? Could somebody explain to us how you have arranged it? How is the cupboard at home arranged? The cupboard for keeping plates and so on. Yeah, go ahead.
Okay. Our cupboard at home, we can arrange it, like for example, the cups, maybe according to the color, the nature, and so on. Then the glasses, we can arrange them, okay, according to their structure.
Have you arranged the plates, glass plates, according to structure? How?
No, the glasses.
At home, in the cupboard. How have you arranged it? Let's take plates. How? Okay, finish and she supplements.
Okay, she can continue.
She can continue. Okay.
The plates, you start from the biggest plate, then you go on piling them to the smallest plate. You can't start with the biggest plate on top. Then the cups, I think the ones that are, when we say breakable, the ones that will be inside, just in case it open, like without.
Is it what is it at home, the cupboard? Okay. Go ahead.
Then the plastic ones will be in front if they are there. Then the glasses will be in their own cupboard and they will be arranged. The big ones will be behind and the small ones in front and side at the beginning.
Okay. Yeah. That means there is a reason why you arrange. Why do you think they are arranged that way?
Because the big ones, most times they are really heavy. And they might then just sit on these tiny ones and end up breaking them. The tiny ones be on top, so that the big ones can carry all that heavy weight.
Okay, that means if we say they go and get a big plate, you can easily get it.
No, you have to remove them carefully.
But you would know where it is. Oh, okay. Yeah. At your home, who doesn't know where things are easily? Among the family members, if you say, look for salt, who might fail?
My dad.
Thank you very much. That the father will fail, not so, because he will not know the location. Now, a periodic table, you recall in senior one we discussed elements. And we listed the first 20 elements. Does anybody remember? First 20 elements? Okay, let me have somebody who is very, very sure you remind us. Yes, Patience, remind us the first 20.
Hydrogen.
You have hydrogen, symbol?
H.
H.
Helium.
Helium is the next. Let me use symbols for space. You said hydrogen?
Yes.
Yes.
Helium.
Helium is which?
He.
He.
Lithium.
Lithium is?
Li.
Li.
Beryllium.
Beryllium is?
Be.
Be.
Boron.
Boron.
Is B.
Yes.
Then carbon.
Carbon.
C. Nitrogen.
Nitrogen.
N. Oxygen. O.
O.
Fluorine.
Fluorine. F.
Neon. N. E.
Yes.
Then sodium. Na.
Okay.
Magnesium. Mg.
Mg.
Then aluminium. Al.
Aluminium. Al.
Silicon. Si.
Si.
Phosphorus. P.
P.
Sulfur. S.
S.
Chlorine. Cl.
Cl.
Argon. Ar.
Ar.
Potassium. K.
K.
Calcium. Ca.
Ca. Yeah, thank you very, very much. That's a very, very good head. Girl seems to be very, very bright. Is it that true? Okay. Now, scientists kept observing different materials so long time ago. Even they thought some elements were compounds. That means it was not very easy, but upon regular studies, they realized how to find that elements are elements, and most elements were discovered slowly. That means it took a very long time to come up with so many elements, of which we claim they are about beyond 100 elements. There are more than 100 elements. See, and more are being discovered. Now, the periodic table was just a way of categorizing these elements, because some of them, when you look at them, some they behave the same as others. Some even have colors similar to others. Now I will ask you to go to Google and look at the color of each element there, especially the metallic elements. You'll say color of sodium, you compare it with the color of potassium. See, you compare it with the color aluminium. You can compare all the colors, the metallic elements. You realize that some have similar colors, some have similar luster. Luster, we mean the way an element reflects light. Does it reflect light and looks shiny, or it looks dull? You see that? The way an element reflects light, which makes it either appear what? Dull, or appear very, very attractive and bright. Now, shiny makes it appear shiny, attractive, or dull colored. See, that's what we call luster. Now, some elements behaved the same as others. You see, some were gases. See, now it made them to come up with a way of saying, let us put elements which are the same together, elements which have similar properties together, similar chemical reactions. How do they react? To react is to undergo a chemical change. If you burn them, do they undergo the same chemical change? See that? Then they came up with what we call an orderly arrangement of elements depending on their similarity in the properties. See, that was they called the periodic table. An arrangement of elements based on the existence of similar properties. Similar chemical and physical properties. See that's very, very important. So now that they were arranged basing on similar properties, and the most important properties there are the mostly chemical properties, because they are what shows that really this element has the same chemical behavior like the other one. Physical properties might differ a little, but the key important properties to identify elements are the chemical properties. Yeah. Now that periodic table, I've given you a book there. If you look at it there, yes, look at it on Holderness, the last page where I pointed you. You realize that that periodic table has some form or some form of arrangement which we can roughly sketch here. To just show our first 20 elements. That means we are looking at the structure of the periodic table for the first 20 elements. Periodic table for the first 20 elements. Now it has, for us we shall not handle all because it is so big as you see. Yeah. Let me have there one material. Yeah. It is very, very big. Yeah, as we see, it is such that there is something here. There is H here, and the Holderness has given the name of each. The name of each very, very well. Yeah. Now that's it. That's it. We are deriving it from here, but drawing a portion of it. Remember, it has many elements. Even it has blocks. There is a block down here of more elements being discovered. See? Yeah. Now, there is a certain unique number that is being used to move that periodic table. There is a certain unique number. Look at that periodic table down here. There is a number there are two numbers up and down. The most important number that was used to generate a periodic table was this bottom number. Do you see that number? Yeah, you see it?
Yes.
Then here there is helium, and it has 2, and it has another number here. You pick that?
Yes.
There is 4 and 2.
Yes.
Now, the whole periodic table is moved like this using the lower number, this one, 1, 2. That means the first 20 elements, if I number them 1, 2 at their bottoms. See, at their bottoms here, 9, 10, 11, 12, etc. You realize that it will match exactly in the periodic table to pick the first 20 elements, 1, 2, 3, 4, 5, 6. It skips, there is this group of elements that behave totally different from others. That's why it's isolated. It can't be numbered among the first 20 because it's very, very different. We shall see what it is called. 12, 13, 14, 15, 16. Then for us, we 18, there is 14, 15, 16. No, there is 11 here missing. 12, thank you. 13, 14, 15, 16, 17, 18. Then we shall end here. 19 and 20. Now, if we put them, we shall realize they follow your pattern you have stated. Here we'll have lithium. Then here we'll have beryllium. Here we'll have boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. Now, see, this number down here, we are going to see it under atomic structure here. We are going to call it atomic number. See, we shall call it atomic. It is, in fact, a periodic table. Instead of defining it as as the arrangement of elements based on similar chemical properties, we can also define it as the arrangement of elements in order of increasing atomic numbers. That word atomic number, we said it is a unique number, see, that identifies most of the chemical properties of the element. See, we are going to dwell on it ahead there to see how does the atomic number play in making an element undergo a chemical change or a chemical reaction. See, now look here. If you look at that textbook, it has labeled here 1, 2, 3, 4, 5, 6, 7, 8. Sometimes it labels this one as O. We shall look, I'll give you some information. Why is it O? There is a reason behind, but it's under atomic structure here. Why is it O? See, yes. Chirabo, you have a question? A correction. Helium is 8. Helium is 8. Here. Yeah, very correct. Great. Now, in here, there are special elements called the transition metals or transition elements. We shall see that they have very interesting chemical properties, or they undergo very interesting chemical properties. See, they are where you find the elements, like you can see them. Copper, do you see copper there? You see, now if you look at, we have a substance there called the copper sulfate. Do you notice that substance called copper sulfate there?
Yes.
What was the color when we saw it under salts?
It was blue.
It was blue. Yeah, that means they form compounds which are colored. That we shall see why are they so unique. Now look here. The rest here will form compounds that are white, as we saw. That we saw there some. We saw some magnesium, calcium hydroxide powders were white, but we shall see that later. See that these ones have unique properties in their behavior. See, now look here. Yeah. If I ask you a question, in the discussion of elements in senior 1, see, we saw that they were categorized as metals and what? Non-metals. See, non-metals. Which metals did you recall? Do you recall?
Sodium.
You recall sodium? Potassium. See, could you now start to look here and you see that all these are metals except the hydrogen. See, that from now aluminium, is it a gas? You know that it's even at home. Is it at home? In the form of saucepan. See? That means we are going to see that from group 1 up to group what? 3 here. That means you have metals. So you have metals. Yeah, that's your real predictable. Group 1, 2, 3 are. Then, see, up to there, these are what? Non-metals. But there is in the middle, because you have 8 groups, 4 is in the middle of 8. So, for them, because they are between metals and non-metals, they have properties between metals and non-metals. Therefore, we shall call them some funny name called the semi. Maybe, of course, they are also called metalloids, the other name. That means you must be very, very keen there. This part is very unique. Yeah. And you must really understand that predictable so clearly that now some groups there have been given some other names because of what they form after undergoing a chemical change or a chemical reaction. See? Did you recall that we talked about sodium hydroxide was what? Was which class of compounds? Was it an acid? It was under bases. And we also further went ahead to say it's an alkali. Now, these elements, the first one are called, some have special names, alkali metals, because they go ahead to form alkalis. See? Alkali metals. That means which of the following are alkali? That's group 1. Now, they are grouped for me sodium metal here. We can have a look. Now we say that when they categorize those elements, they will have similar properties. See? the color might be the same or it might vary. See, but the chemical properties are the same. Now, if we look at sodium metal's color, it will indeed spatula. It will indeed sodium metal will like others. So yeah, sodium. Now I will remove it. I hope they didn't take back our petri dish. Now this is sodium metal. It looks whitish because outside it is always affected by air. But I want to demonstrate. I'm going to cut it with a spatula's end, but I can cut it with a knife. A knife. It can be cut by a knife. Now, did you believe that metals could be cut by a knife? That beaker? Can you cut these things with a knife? But there are some weak metals that can be cut by knife, and they are under which group there? So, yeah, if we cut this sodium metal and you look here, it has a shiny luster. That shiny appearance, we are calling it shiny luster. You see that it's shiny. Which color is that? If freshly cut is which color? Silvery. Some white is there. That means the color is silvery white. See? Silvery white. Now all group 1 elements will be silvery white. I hope that's clear. That's very, very clear. I am emphasizing colors because in chemistry, under chemical reactions or chemical changes, colors are very, very paramount, are very, very important in chemistry because they show us that something has taken place. Yeah, we have said group 1. Now you see some of these elements. Listen, this is magnesium ribbon. Magnesium ribbon. It's coiled in this form. That's why they call it that kind of a name, magnesium ribbon. So it's a what? Now, if you look at it, you see this metal, it is appearing black. But indeed, you see, it's not black. It's because you see these metals, they tarnish. Like that sodium metal, when we leave it exposed, that shiny luster will disappear. It will become dull colored because air attacks it and it undergoes a chemical change. See? Now this one is blackish in color, but which indeed it is not. But when we use sandpaper to try to, you have sandpaper?
Yes.
The one the carpenters use for smoothing, even painters, walls. Now you can pass it over here, then it will have a shiny luster. But it will look, if we tried to scratch it a bit, it would have, it has that silvery gray appearance, silvery gray. That's magnesium ribbon. So that is taking you that group 1 will have silvery white color, silvery gray color. Color is so important here in chemistry. Mark that, because we shall ask you ahead there, and when we are looking at some reactions, we shall see magnesium after reacting has turned from which color to which color. See, and each time we shall not be bringing you in the laboratory to see the colors, no? But upon knowing that magnesium is silvery white, the rest have the similar color. See, that's right, that's right. So, yeah. We shall see that aluminium also has a silvery white color. Some silver white. Silver mixed with white. So, phosphorus, as we shall see, carbon, we shall see carbon ahead there under carbon and environment, one of our topics, and see that charcoal is carbon, which is black. That can tell you the color of these elements. Phosphorus is in two colors, red and white or yellow, three forms, three colors. Sulfur is yellow. That means we can now follow, and those are some of the appearances. Oxygen will appear in form of a gas. You know, oxygen gas that you breathe in, you know its color. Is it blue? Colorless. That's right. See. Now look here. See, you see the pattern of placing them in groups. This is group 1, group 2, like that, 3, 4, etc. Now horizontal alignment, horizontal placement. If you say 1, 2, 3, horizontal counting is called period. Yeah, there you are. There you are. But this is period 1, period 2, period 3, period 4. That means the periodic table it is arranged in form of, say, groups and periods. Now I will ask you, how many groups do you see in that periodic table? 8. How many periods do you see in that?
7. There are 4 periods.
How many? Not the one you have there.
Yes, sir.
See. But mine has. That's 4. That means the maximum periods for the first 20 elements is 4. Yeah. Now, that's it. Now, under periodic table, we have chemical families here. Chemical families. Well, what is a family in your English? What does the word family mean? A group of, see, therefore a group of elements with similar chemical properties is what we are calling a chemical family. I think you see. You see? That means our chemical families can be group 1, a group of elements with similar chemical. So that's correct. So, yeah. Yeah, I love that subject. So, now, which chemical families do we have? Group 1, group 2, 3, 4, 5, up to 8, and another chemical family is transitioning metals or elements. What is the reason for grouping them? Similarity in chemical. Do we understand when we say chemical properties? See, we mean when we conduct a chemical change like burning in air. See? Now, look here again, because we are trying to close down the periodic table. Look here. These are called alkaline earth metals. Group 7 are called halogens. Those names we are putting them there as we shall interact deeper. Group 8 are called, you know some of the, what's that name there? What are they called from air discussion in senior 1? Yes. Rare gases. Thank you very much. They were called rare. See. Or noble. See. Noble or rare. See. Now look here. There is something I want to really emphasize here. Why are those up and some are down? See, look. Now, in the arrangement of this periodic table, the most reactive elements are always placed on the right, on the left, if they are metals. See? For metals is 1, 2, 3. Reactive metals are in a group, and the order is that way. Clear? If you compare reactivities, most reactive is group 1, group 2 is next, group 3 is last. Now under non-metals, the reactivity is in an order of that same form, that as you go this way, they become more reactive. See? Except group 8, which is unreactive by nature. By nature, they don't react. The reactivity is from group 5, 6, 7, and as you move like this, group 5 is less reactive, increase in reactivity group 8, group 7 are the most reactive elements among nani? See, let me overemphasize something here. Now, from up to down, for metals, reactivity is up to, reactivity increases. Oh, that means you can say that potassium is the most reactive among group 1 elements. See, you see that? See. Now, for non-metals here, the most reactive is now what? Up. That the reactivity of metals is opposite to that of non. See, that non-metals react more going up. More going up. See. Yeah. Up, fluorine is the most reactive. See? Should be very careful, because some of these things we just rotating on this. I'm putting them at your attention because we shall meet what we call reactivity series, so that I will be referring to the things that are hanging in your head. So, to react. So,
is it fluoride or helium that is more reactive?
now, Non-metals, there is a group that is very, very awkward. It does not react at all. Have you ever read any compound called neon chloride? No. It can't exist because for them they will occur on their free state on their own as themselves. You'll never find them in combined state because they are called noble or unreactive or rare. See? That means the reactivity of metals is gauged, of non-metals is gauged from group 5 to group 7. And it increases like this, meaning chlorine is most fluorine is the most. But in comparison across, you see that fluorine is more than any element before it. See? Yeah. Okay. Other things we shall meet them. Chemical families, we say the group of elements sharing similar chemical properties, and we have said they are just those groups. Group 1, 2, 3 is what the groups is what we call the families. So yeah, that is that on the periodic table. You will receive some revision questions at the end of the chapter. It means, see, I can put here a sample testing question to check before I drop onto the atomic structure. See, now, did you notice that periods are written using the normal numbers 1, 2, but when you are saying group 1, you don't say, when you say group 1 like this, that's not the scientific way of representing. It is Roman numeral. See? Yeah, let me put for you here a sample question, very just brief question. Here you answer it and try that the diagram below shows part of periodic table where the letters are not usual symbols. Yeah. Now you just take very minimal time. You discuss over this. That is that is 1, 2, 3, 4, 5, 6, 7, and 8. See, X and Y. So here we can have A, B, and C. Which one is the most reactive metal? Most reactive metal. Non-metal. See, part B lists the group of halogens. 2 noble gases, noble. gases. Let me, it is you to take over. See? Yeah. The answers must be in terms of those letters. Don't again say, don't again do what? Don't again go and pick the elements from your head that you have in the periodic table and transfer there. Yeah. Can I have answers now? You speaking now. Question 1. Question A. Who is taking over that? Chirabo, take over.
Which one is the most reactive metal? It's metal X.
X. Because
reactivity
increases
downwards.
Down the group.
Then the non-metal is C.
C. Because
Reactivity increases upwards.
up the group. See. List the group of halogens. Which elements belong to those halogens?
C and D.
That is C and D in group what? Group 7.
C and B.
C and B in group 7. Noble gas?
D.
D in group
8.
8. Or group O. Yes.
But if they say list in their group, meaning you must indicate those elements inside the group and give also
The group.
Okay.
Group 7, C and T. So that's all. Let us drop. There are many things here. Let us drop to an atom, atomic structure. You must be very now. This one we are going to pick it from Google. Now listen. We built an atom. Where does the concept of an atom originate? It originates. Can you take over that? Where does the atomic concept come from? Is it something that is found? Is it a thought? What's an atom? And where does it emerge from is very important to us. Yes, Chirago, you want to take us through what's an atom?
An atom is the smallest indivisible unit that takes of an element that takes part in a chemical reaction. And an atom comes from matter.
Patience, do you have another view? That it makes up matter. Yeah, that's correct. Yeah, smallest indivisible particle of an element that is capable of taking part in a chemical. Yeah, like if you are, I've given you sodium metal there, which is sodium element. Therefore, don't ask that now, where do I find an element? No, I've given you an element called so. And what makes up sodium element is sodium atom. See? So, yeah. Now, that definition of an atom, you are aware. Now, structure of an atom. Can it be seen? That means the metal I've given it there is built from many atoms called sodium. You see, somebody might think that I've given you one atom there, no? I've given you millions of unseen things that make up a seen thing called sodium element. See, now from Google, we can find out that the atom, but some of you have consultative materials there. What are they saying about the atom? Oh, how does an atom look like? Those who are using Google can use Google. So, we see that the atom is represented like that. But that concept of an atom took scientists several decades. The father of atomic structure was called Dalton. Yeah, he tried to find, but he tried to think through an atom, and he told us that an atom is like a ball. That a ball, you know, a ball that you even play in the field. He said that atom is like that. See, that was a very big struggle to come up with the actual atom. But an atom is said to have a smaller region called the nucleus, and that nucleus has what? You've researched protons and neutrons, not neurons, not so. Then outside here, it has what we call an electron, and in representation electrons we can use arrows, or that means when you see us using an arrow, a cross or a dot, don't worry, we are still speaking about the same thing. That's very, very right. See, that means we can either put this to mean electron, or we can put this. Clear? See? Now, the atom has a nucleus, and it has a space around it that we call energy what? They are sometimes called what? Cells or orbit. See, nucleus. It has, P stands for protons, small n, not capital, neutrons. E is L. See, now you see, we can't say that let us start going in the lab, then we get an atom in the laboratory. You will not see it there, but you will see things that are made up of atoms. Now, we cannot have where to access that atom. Therefore, don't say that, teacher, I want to see it. We said it can't be seen because the great scientists began cutting a paper. He cut and he cut and he cut a paper, and he cut and he cut and he cut the smallest. He kept on cutting. What did he cut finally? If you cut a paper into 2 pieces, you cut again the pieces, you cut and you cut and you cut and you cut. What do you cut finally? You see nothing that you are cutting. It means you are ending up into a world of atoms. See, when you enter invisible things, then you are entering into. See, that's why when a chemical reaction is taking place, you cannot know by use of eyes what has taken place inside, but you just see change of colors, change of structures. You see, because the reaction things occur, because you would now say, maybe this is bending. You don't see those things because atoms meet invisibly. See? Now these two that appear in the nucleus are called nucleons. They have a basic name, nucleons. See? Okay. That throws us to fundamental particles of an atom. Fundamental particles of an atom. Now we see that the atom has three key particles, which we call protons. See, now from Google, I'm emphasizing Google because it's where we are going to get those things and in those books. See, particle, the charge, and the odds. Oh, that's right. Now, if the atom has those particles, you see, the first particle is called a proton, a neutron, and an. Now, Google's research. That means you type in what we charge of charge on the proton. It will show you the charge on a proton. See? That means you will have protons positively charged, the neutrons no charge, electrons are negatively charged. Protons weigh a mass of 1 as well as neutrons, but electrons have negligible mass. Does it mean the mass is 0? No, it is there but too small to be ignored. It's almost not there, but it's there. See, now listen very attentively. Now every atom has the same number of protons and electrons. Did you hear that? Now let me ask, what is the overall charge on an atom? Is the atom positively charged, negatively charged, or neutral? Neutral, because that means equal number of opposite charges will cancel. Thank you very much. That means every atom is neutral. See? Yeah. Now, symbol of Annie. There you are. That's very, very great work. There you are. Do you see in our periodic table the atoms representing each element, how they were labeled? How is that periodic table written for, let's take an example of lithium. How is it written? 7 is up. 3 down. Sodium? 23? 11. Now Mark, look here. See, this 3, we say the bottom number was used to locate elements in the periodic table, and it was called atomic. And up now, atomic number up, we call it atomic mass or mass number. Or mass number. Now, look here. Did we say that the atom has how many particles? Protons, neutrons, and clear. See? Now, this 3 is also called the number of protons. that is puzzling your head. See. Now, because now we want now to build, we are going to build and locate the elements in the periodic table directly from these things. See? You see that? And you see, when they represent like this, all the particles are catered for. See? Let me ask you. The mass of any atom is determined by what? From the previous discussion there on the fundamental particles. The mass of an atom is determined by which particles? Be loud, patience. What is that mass determined? Who determined the mass among those 3 particles? See? Because you say the protons have a mass of 1, neutrons 1, electrons negligible. See? The mass is determined by who? The neutrons and what? Now, that is the mass number means the mass of the atom, which is up here. Now we are going to start our definitions here. See, I'm removing this to make the information more elaborate. That an atom is symbolized with 1 number up and 1 number down. The general symbol of any atom is a number up and a number down, in which A is called mass number and B is called atomic number. And the atomic number is simply number of protons. See? Now listen. Let me ask. If B is number of protons and A is protons plus, see? Because they are the ones that determine the mass of the atom. So, now, how do you get number of neutrons? See, look here. Let me remove this. Let us first define here that atomic number is the number of protons in the nucleus of any atom, because protons are located in the nucleus. Mass number is the sum of protons, the sum of the number of protons and neutrons in the nucleus of an atom. Do you get that right? See, those definitions are very, very important, especially in assessment. Define mass number, the sum of the number of protons and neutrons in the nucleus of an atom. Why? Because the mass of electrons is negligible. Atomic number is the number of protons in the nucleus of an atom. Now, how could we get the neutron, the number of neutrons? How do we get number of neutrons from these 3 things? And also I'm going to ask a question. How many, in case you had lithium here 73, what is the number of protons here? Protons are what? 3. The mass number is
7.
what are the number of neutrons?
I think
There are 4. 3.5. 3.5, 4, and 4. How did you get 4?
because if the number of protons is 3 and the mass number is 7, so meaning you have to subtract the number of protons from the mass number to remain as the number of neutrons.
Are you still supporting your answer of 3.5? How do you get 3.5?
Mass number is made up of protons and neutrons.
Exactly.
And 7 is the mass number. So if you divide 7 by 2,
You are trying to tell us that the atom has always equal number of neutrons and protons. Is that correct?
I'm saying yes.
You see, now the truth is that neutrons can't be equal to protons. It's electrons that are always equal to protons. The neutrons are got by subtraction from the mass number. That means mass number minus atomic number is giving you neutrons. See? Yeah. Now you will have that assignment. First 20 elements. Protons, neutrons, electrons, then the mass number here. Now, the first 20 elements, you locate their information from the periodic what? But the first one is hydrogen, helium, not so? Lithium. The next one is what? Lithium, beryllium. You'll fill the first 20 elements, their mass numbers, and did we say that proton is also called the atomic number?
Yes.
Yeah. Now you'll hear like hydrogen has 1 and 1 in your periodic table. Clear? Then it means the atomic number is 1, mass number is also 1.
Then does that mean it doesn't have a neutron?
That's the meaning. Helium had 2 and what?
4.
What are the protons?
2.
Neutrons? Electrons?
0.
See? There you are. How many electrons does it have?
3.
I think it has 1.
Which one? Hydrogen. Helium has 1. How are you getting electrons? That's really very, very fast, is there? But let me ask you, is an atom neutral? Why is the atom neutral?
Because it has both positive and negative charges.
You are not speaking. Now, if I have 2 positives and 3 negatives, am I neutral?
Yeah.
Why is it neutral?
I think it's not neutral.
It's not neutral.
I think it's
But some few minutes back we said it was. Why? See? And we said it has protons are always equal to what? Electron number is equal to proton number. And since protons were what? Protons were positively charged and electrons are what? Negative. Therefore, proton number is equal to electron. Do you see that? Because every neutral atom, it simply means positive charges which are caused by protons are equal to negative charges caused by. Now you will fill for me the first 20 elements and you put their respective information there. Now I'm now running to here. I've finished. I'm running to isotopes. Isotope, then I go to configuration here. See. You see, the whole atom is made stable or is made to exist without disturbance, because positive charges are attracted to negative charges. That means the whole structure is compact. See, because we say the center, let me ask a question. Protons are positively what? Electrons have no charge. Neutrons have no charge. Electrons have a negative charge. See, now, when the atom is existing, from our primary we saw that unlike charges attract each other. See, now that means there is a binding force due to attraction within the atom itself, that's why you might say the electron never falls off a shell. It can't rotate and fall off because it is always supported by the attractive force from the nucleus. See, the nucleus. So now dropping down to isotopes. Now I want you to watch here. That means be very, you see, these things are very, chemistry is very, yes.
Why do some elements have points on their mass number? Like 35.5.
Yeah. Now that mass number is determined by an instrument. See, it's not, did you think they are just guessed? You see, they are not. See, they are determined by an instrument, and when the instrument determines, it gives you information from which you can calculate the mass number, and by calculation you can get a decimal point. But at this level, that means if you are going on with that chemistry up to advanced level, you are going to look at that machine of determining the mass number. See, that's very, very interesting. Now, isotopes and isotopy. See, I want you to, you see on Earth here, you can find chlorine, you can find certain elements which have more than one atom representing them. Listen, we are saying that elements having more than one atom representing. How could we say that? That the president of a country can send 2 representatives but they are representing the same person. See, some elements, not all, see, can have more than one representative. Clear? Now looking here, that chlorine, like for instance, we shall pick those elements which have those unique properties. Chlorine is there. What does your periodic table give him? Mass number?
35.5.
35.5, but we shall use 35 there. That one would mean if you rounded it 36. But for us, we shall use, do those both periodic tables show the same? The other one? 35.5? This one?
Yeah.
The other one?
Yes.
The big one? 35.5. Now, we are going to use the 35 to talk about something here, and 37. But what is the atomic number there?
17.
I've left that middle number, not so? I've picked 37. But here it is 17 both, not so? Chlorine has 17, of course. I've removed this. Now, look here. See, on Earth, chlorine, that means you'll find chlorine somewhere is representing chlorine, this one. This one represents this one, but at 35, 17. This same one can be represented by 17 and 35. Remember, we said to place you in a periodic table, we use which number?
Use the
Atomic number, that one. That means the atomic number cannot change, but mass number can. That's why you realize that elements, those with decimal points, most will have more than one form representing them, so that by calculation they will always give something of the sort. See, you'll find there are others with some decimals, but it is just from their calculation which gives them their average mass. See. Now, let us narrow to this one to explain what we mean by isotopes and isotopy. Now, we've said an element can have two representatives, but we can say that both are chlorine. Why? Why should we say both are chlorine?
Because they have the same
Atomic is the major identity of the element despite a change in the mass. Now, the two representatives of the same chlorine are called isotopes. See? Then all elements which always have more than one representative are called, they are said to show isotopy. Now we can put correct definitions now. That isotopy now is the existence of what? Is the existence of atoms of the same element having the same what? Existence of atoms of the same element having the same atomic number but different mass numbers. Can you find out what brings in the difference? See, which other particle is bringing in a difference there?
The neutron.
The existence of atoms of the same element with the same atomic number but different mass numbers, which is due to the difference in the number of neutrons. Clear? Then what is the meaning of isotopes? Who can define for us now what are isotopes now?
Isotopes are elements with the same atomic number and having different mass numbers constitute a neutron.
See, now you see, you said they are elements. See, Now, what are we talking about here? The symbol of Ani? Because anatomy is what represents the specific element. Yeah, that's correct. Now, I think that's mastered. Clear? See? Now, there, let me go into depth. Get the definition of isotopes, and you see. Chirabo, you're saying something.
Isotopes are atoms of the same element having the same atomic number and having different mass numbers caused due to the neutrons.
Neutron difference, not so? Okay. I think you capture, I think that's correct, not so? Thank you. Now, elements which show isotopy, we said not all of them, no? But we have seen the first one is chlorine, not so? See, elements that show isotopy, like chlorine, how many isotopes does it have? Chlorine 35 and 37. We read it. We read it from what? We read it from. How do we read? I think you're seeing me read the chlorine 35, not so? Now this one is read as what? Oxygen 16. Now it does not mean that, you see, we say to have a decimal point, mostly you have isotopes. But it does not mean that all that don't have. See? That's right. Your phosphorus here, for it is red. It has just what we call red phosphorus. And no, that's it. That's a bit. That's a bit. Me, I will report it to and request for more from our Google Earth search engine. Yes.
Why do some elements here have a mass number?
Say it again. Say that statement again.
Why do some elements here have mass numbers?
Why don't some elements have mass numbers? It's not true. Look at this book, Holderness.
No, this one doesn't have some elements that are here.
Because I think there are just many, not so. Which block? The lower block down?
No. There are 105 to 109, and this one is also 100.
You see? But you cannot place them. It doesn't have mass numbers or atomic.
Mass.
See? Does that cause a puzzle in your head?
No, I'm just wondering.
You are wondering.
Why they never put them there?
Okay. That could you give a reason? Could it be machine error or they don't have natural? Now that one will be left for Google. You'll compare several periodic tables, but I have some here. I think the reason might be congestion, but everything on every element that is developed in the periodic table has been tested. You see, in case you read so much and you went into inventions until you discovered an element and maybe you called it what? Your name, not so? or Patience or Chirabo. Then you'll be asked to defend. You'll be asked to go ahead and defend that what? The element. But you must have tested its atomic number, discovered it, mass number. You'll have determined it. That means no element can be placed without. That might be intentional printing what? A printing intention. Let us drop to electronic structure or electronic configuration. Now let us move class, because we don't want to overbear much here. Electronic structure. Now, it just means the arrangement of electrons around the nucleus of an atom. Now, the arrangement pattern is such that steps of arranging electrons, steps of arranging what? Electrons, arranging electrons. Now, see, electrons, when they are being arranged here, it was already formed for us. Therefore, we are just enjoying that. Every atom, you know that it had what? It had energy levels, not so? Now, if it has energy levels, meaning electrons are arranged in energy levels. First energy level or first shell
Maximum of 2 electrons.
takes up how many? Takes up maximum of 2
Electrons.
That's from your research, not so?
Yeah.
Second shell
Maximum of 8.
takes up maximum of 8. Third shell takes up 8, not so? Yeah. Now, in drawing, we can draw the structure or we can write the structure. That means you can either draw or you write, not so?
Yes.
Yeah. Like if you took an example of, say, sodium 2311. Its center, then it would have the first energy level, the second energy level. This has protons and neutrons. How many? That means a compass is used for here. The first one we put how many? 2. We can use a cross or we use a dot, zeros, or you use the actual E. See. Now the next one takes how many? 8. And the electrons always sit in pairs. Did you hear that? They sit in pairs to stabilize, to make each other comfortable. We call it stabilizing each other. How many are remaining? 1. Therefore you put it there. See? In writing the structure now, how? 2 to 8 to 1. Now, I want to ask, if I wanted you to give me the atomic number of say what, aluminium, are you able to give without anything that you have there?
Yeah.
How? 13. How?
You can use its position in the first 20 elements.
The first 20 elements by saying 1, 2, 3 up to 13. It means what you are counting is the atomic key. See? So, yeah, that's very, very good. Very good. So, yeah. Now there, it is about to throw you. About to throw you somewhere. You see, these things are very, very connected. You see how things are very connected. The entire periodic table is, you see, it is going to now, it is going to move here and show us how now we can, how the elements were so placed in the periodic table. See? And if you follow those who are going on with chemistry, which I pray that you go on with, and I believe that you will, not so. Now, you realize that you will just keep expanding the same atom. You just keep expanding. See? You can try for me oxygen 16 here. If they say right, you write. If the question is draw, you what? You draw. See? But of course you'll find other forms of writing where you can use a kind of a what? Like somebody can say 2 like this. This is the same thing. See? That means you can say this or this, your preference. Preference. What is the writing, patience?
2 to 6.
2 to 6. See? Now, don't rub those things. I'm now shifting to stability of an atom. Also, capture for me helium. Helium is what? 2 and 4. Write for me its structure there. It's only. Now wait, listen. First shell takes up a maximum of? That, you see, to take up a maximum of 2 is to be totally filled. You can't add you more. You are satisfied at that point. Clear? Now listen. You see those electrons that we are writing there? We are not just writing them for the interest of writing them. No. They are you see, when we put here an electron, this is a specific place an electron is sitting in. Like if we are looking for you, if like I was at home and I was locating a person to come and look for patients from home there, or look for Chirabo, I would say, go to Seta. Look for a place called Seta Hill. Go to the room behind. Not so? Isn't it where you stay? Now, look here. Now, when we place an electron, it is in a particular place where, and those places in the first shell are finished. See? And in the second shell has how many places? 8. See? Now, you see, when the atom receives its shell at that level, all the electrons, it is said to be stable. It needs no more. To be stable is to have almost whatever you want, you need nothing. Not so? Now, yes, patience, you have a point?
I have a question. Here the periodic table, on some elements they can put 2 to 8 to 18 to 18 to 6.
See? Now, wait. They can put it to 8, to 18. Where did you find it, on Google or in a textbook? Textbook, fine. Now, that's why, listen, our discussion limits us to a maximum of how many?
8.
Our atomic number what? It limits us to atomic number 20. Because when we exceed, it calls in some chemistry which we are not able to discuss now. That's why ours for calcium, calcium would be what? This has configuration of 2, not so? Calcium, which is the last element, would give us, you work out, configuration. What is the configuration on writing it? Do you need it to draw? You can work it out logically in the head, mathematically. As you add, you write as you add. Total?
8 to 8.
Total.
Yes.
Now look here. Don't grab that part. I was saying to be stable is to be fully filled with the maximum that you can have. Listen, see, you must be following these statements, because here you say 2 to 8 to 8 to 2. Now, what if you were writing for neon? Neon is what? 10.
Yeah.
Right. What would you write? 2 to 8. See, now, you see, look here. The first shell has 2. Helium had only 2. Clear? And it means, since it has no more electrons and it only has 1 shell, therefore it is stable at that point. Is oxygen stable? Why?
Because it has more than 1 shell.
Because it has more than 1 shell.
And the second shell that it has is not complete.
Do you really agree?
Yeah.
You see, that if you try to exceed 1 shell, then the shell you end with should have what? 8. See, when you have 6, you are less. See, it lacks, it is unstable. To lack is to be. Now, don't grab that. Let that be at your attention as I shift to stability of an atom and ion formation. We've said you are stable if your last or outer shell, if the outermost shell of your electronic structure is fully filled. And to be fully filled is to have 8. Or to have 2 in case the atomic number is only 2. Clear? See, now when the atom is not stable, then it will change into what we call an ion by it making sure that outside is full. See, by making sure that outside is now look here. You see, when you let's say, when assuming you are lacking, if the school is paying school fees of 1 million, then for you lack your two friends, who Chirabo and Patience, but Chirabo lacks 100,000. She has 900,000 to make 1 million. Then Patience has only 150 in the pocket, and she's lacking around 850. How will Chirabo become stable? Who will help the other? But how?
Patience will help.
Patience must give you. You lack a little. It is easy to compensate little by being given. That means the one who has much remaining has to lose. See? Look here. Look into this, and you look into this. Sodium. Sodium out lacks 7 to become 8. Clear? Whereas this lacks 2 to become. That means oxygen will always gain 2, but sodium will always lose the last one, so that 8 is out at the last 8. See? That means atoms with very fewer, see, below half of what you need, you will lose. Above half of what you need, you will gain. Half of 8 is what? 4. That means above 4, you must be given, but below 4, you must. See? You see that? Now, let us put that clear, and we emphasize, then we drop to electronic structure and the periodic. You see, we are going now to connect all these things to a periodic table. And now you will see how that same writing can locate an element the way Mendeleev, Dmitri Mendeleev, was the father of the periodic table. Who discovered the periodic table? Dmitri Mendeleev. See, he really discovered it. It's called the modern periodic table. See, now we are looking at stability of an atom and ion formation. Have we emphasized the stability? When are you stable? When the outermost shell has either 2 or 8. And to have 2 must be a condition that your atomic number is only 2. Clear? See? Now ions are formed when atoms want to become stable. See? When atoms want to become stable is what makes the atom to do what? That's what makes the atom to lose or gain electrons. Then we have said we have ion formation occurs when atoms want to gain stability. Have we said so?
Yes.
Then have we said now here we shall have formation of positive ions, and those positively charged ions are called, let me write it well here. We can either form positively charged ions. In chemistry they are called I don't know, how do you read that? How do you read that? Cations. Then negatively charged ions are read as. Now those are a bit funny. Now look here. Look here. When an atom loses electrons, it becomes positively charged. See? Oh, that's why we talk speaking about hydrogen and the other time. I can remember in acids. Not so? Do you also remember the same?
Yes.
See? Now look here. That e.g. sodium 2311 electronic configuration would be 2 to 8 to 1. Now sodium ion, that means sodium ion is formed when you have lost what? Electrons. How many does it lose? 1. Therefore sodium ion will appear positive with 1 positive. Then the electronic configuration of this one is for the atom. Then the one for the ion would be who can guide us? What is the electronic configuration for the ion? For sodium ion. Because this is for the atom. This is not so. After losing, not so. Yeah. Now we want to tell you that now if we think mathematically here, you see the atom has not lost protons, no, but it has lost electron. Listen there. The atom hasn't lost the proton, but it has lost the electron. And originally, how many protons are there? 11. Protons don't change. See? But it has lost how many? Protons are which charge? Now, how do you calculate the charge? You locate back at the protons are always positively what? Charged. Pencils, are we together? And electrons are always negatively. How many electrons do we have now remaining after losing? -10. Total charge you get. And that's how the positive comes about. It can be an interpretation of this electron, or you add mathematically. Proton number positive plus electron. Now we have said that you lose electrons when the outermost shell has either 1 below 4, 1, 2, 3. When it is 1, 2, 3, you lose. See? Then that means what is the can somebody figure out what is aluminium's charge, the symbol for its ion? What charge do we put on aluminium?
It's positive.
Which charge? Which positive?
Positive ion.
Which positive will I put? How many positive charges will it have? Because it is 2 to
8.
therefore it will lose. You will have this. You see?
So is it okay if the positive comes before the negative?
You see, there are what scientists agreed about. If we change, we shall be going against fellow scientists. Okay. Yeah. Now negatively charged ions are formed by gaining electrons. Clear? Are formed by gaining electrons, which occurs when the outer shell has how many?
More than 4.
That is 5, 6, 7. Why can't 8 lose?
Because 8 is stable.
That means you see neon is in group 8 and it had what? Neon was 2 to 8. That's why, you see, that's why this is a group 8. This is a group 8 element, neon. Why? Why is it not losing? It is stable. Now to lose, if you are able to lose electrons or gain electrons, then you are, because the process of losing electrons or gaining is what we are saying, you are reacting. You see, now we are speaking another language. To react is to either gain or lose. That's why noble gases are stable. To be stable is not to be disturbed, to want nothing. See, therefore they don't react, they don't want to engage in any reaction because they are very stable. Now could you now write out for me, provided with oxygen 8, let me use nitrogen, nitrogen 7 and 14, configuration of the atom, then electronic configuration of the ion, then the symbol of the ion. 3 things. 3 things. I will pick one of you to You finished? Okay. Yeah. What is the answer here?
2 to 5.
2 to 5.
Then there is 2 to
2 to 8. Yeah. Then the formula for the charge, the ion.
So small nitrogen.
To power.
To power negative. 3 negative.
3 negative. Very correct. I think you can trace back where we spoke of an acid releases hydrogen ions, and you can figure out why where it came from, because it had 1 electron which it just lost to become H ion back at the iron acids. Now look here. We want to look at how, and this one was and the electron structure and the periodic table find. Yeah, we want now from a written thing like this, can we place the element from a written configuration? Can you place the element? See, me, I'm going to ask you. Here was boron, aluminium. Sorry. remove this. Aluminium, this is beryllium, magnesium, 12. I think I'm interested majorly in the atomic numbers because the mass numbers are not important very, very much. Yeah? Is that fine? Yeah. They are not very, very much. Now don't join element. You see when you're writing these symbols, don't join. If there are two, you separate the letters very, very well because you will not be accepted to write conventionally when you have joined the symbols. If there are two letters, one, the first one is what? Is the first one is the first one must be big, capital. Now look here. Let us try to look here. If we were writing the configuration, say Kalisha with 20, you would say 2 to 82. 2 to 82. I should is 20. To 2. Then potassium 2 to 8 to 8 to 1 also. Then what if we wrote for oxygen? 2 to 6. Then if you are writing for chlorine 17, 2 to 8 to 7. Now look here. Calcium is in group what? Group 2. Not so? Potassium is in group what? Here, not so? Oxygen is in a group? 6. Chlorine is in a group?
7.
What do you really see on those configurations? Do you notice how this being in group 1 here is related to this, and this being in group 2 here, it is related to this? What do you see? It's patience.
Calcium being in group 1, the last shell is 2, and oxygen being in group 6, the last shell is 6, so oxygen will get 2 electrons from calcium to make it stable, and calcium will
Period. The group number is equal to the number of electrons in the outermost shell. You see that? So group, this is 7, but when we say write the group, you'll have to write it group 2 in Roman what? Now what is the period? Is it that we can tell both the group and? You see, calcium is in period what? Potassium is in period. Chlorine is in period. Now here there was this line must join here. Sorry. Period 3. What do you notice? What do you notice? Well, how is the period becoming 4 and yet it is 4?
Calcium is in period 1, it has 4 shells.
That means a group is determined by the number of electrons in the outermost shell, whereas the period is the number of shells containing the electrons. Not so? You just count 1, 2, 3, 4. Clear? See? Yeah. That's correct. That's correct. Now, let me ask. Can we write configuration without these numbers shown to you if you are again a periodic table? Now, have you captured this concept? The location, the period is the number of shells, not so?
Yes.
Then the group is the what? The group is the number of electrons in the outermost.
Yeah.
See, now look here. I'm rubbing out this and ask. We write configurations without them. I'll make sure you don't recall them. Let me rub them. How can you write electronic configuration without them? Now we are moving to valency. Very, very fast. And now, how do we write configuration here in case the periodic table is provided? Like if you write electronic configuration of each. Of each. Of each. Of each. Like if we say write configuration for sulfur. We say the configuration has two features connected to a periodic table: number of shells and the outermost electrons.
2 to 8 to 6.
You help us, you 2
To 8 to 6.
to 6.
Yes.
You'll explain that.
Because sulfur is in group 6
Is in a group 6, which is this,
and it's in the third period.
as in period 3.
Yes.
Yes, perfect, perfect. So, that means you just know how many shells, then you first place the last electrons. Finished. Now I'm jumping very fast to valency. So, it has been a long session. Now you see we are going all the way up to now chemical formulae. See? See? See that? Now the real chemistry is now moving. See? That means you must, all these things are built down. I see. Now, look here. Now we are on valency. Valency. So, now, under valency, I'll start by something that is quite a problem. Water has this formula. I'm discussing now the next subtopic, valency, because now valency will throw me direct to the chemical formula. But it sounds to my head that there is still, if I asked you to write the charge, the symbol for sulfur ion formed, you know that will it gain electrons or lose?
To gain.
Does it mean non-metals always gain electrons? See, that means non-metals are always receiving negative charges because for them they will always gain, will always become positively charged. That means ions for metals will be positive charges because they will always lose. See? That's why when you see us writing K positive, that's potassium ion. Now shift here to valency. In the discussion of valency, look here. This is the formula for water. And now you figure, now how did that formula for water come about? See? See? Oxygen has combined with 2 atoms of hydrogen. Listen, the wording is saying oxygen has combined with what? See, now this figure 2, the number of hydrogen atoms an element combines with is what we are calling its valence. See? And how do I know valency? That valence is the number of hydrogen atoms that one atom of an element combines with. See? See? You must follow. See? Now look here. This 2 will be called the valence of oxygen. See, oxygen now has a valence of 2. You don't put a charge here first, no. Of course, you will see the relationship of the 2. The charge and the valence will be connected. See, now look here. I want you to look here. Oxygen is 8. What is the configuration? Total 6. Clear? And we have seen its valence is what? Now look here. Chlorine is 17, which is 2 to 8 to 7. Has a valence of 1. And that one I'm going to explain. See? Nitrogen is 14. Has a valence of, and nitrogen is 7, which is 2 to 5. Has a valence of 3. See? Now, as we said earlier, see, any atom becomes stable if it, you see, look here now. We want to explain 3 things at once. See, we said you gain electrons when outside you are from 5, 6, and 7. That simply means when you are in group 5, 6, 7, you lose electrons. When you are in group 1, 2, 3, because this 1, 2, 3 is the outermost electrons, then that's group 3 for metals. 1, 2, 3 is metals, and for them they lose electrons because the outside will have 3. Clear? See. Hope you are taking down note of those things. Electrons are lost if the outermost electrons are either 1, 2, or 3, and it means that the group is determined by the outermost electrons also. Now, in simple terms, Now, valence for non-metals, that means from group 5 to 8, is got by subtracting 8 from 8. Group number minus 8. 8 minus 7 you get. What of these ones? 8 minus 8. That's why they are called group 0, because their valences are 0. Now valence, we've defined it, the combining power. I want to explain deeper and now go to formulas. It's the combining power, of an element, or it is the number of hydrogen atoms. One is the number of hydrogen atoms that combine with one atom of any element. Yeah, that's right. That's right. Now look here. Let us exhaust here in depth. I will say it for what? For metals, that is group what? 1, 2, 3. Their valence is equal to the group number. Did you hear that statement?
Yep.
It means their valence is the group number. If you're in group 1, because you have one electron out. But for non-metals, your valence is got by subtracting from 8. See, e.g., for metals, the valence equals the group number. If you are looking at sodium with 11, what's the configuration? 2 to 8 to what? What is the valence?
1.
The group is also?
1.
Period is? Now,
Period is 3.
see, group 1, period 3, valence 1, the symbol of the ion is sodium plus 1. Valence, I will say it is what? See? Now, magnesium, look at magnesium here. 2 to what? 8 to 2. Valence? See? So, now, non-metals, now we are moving. Non-metals, that's group 5, 6, 7, and 8. 8. See, their valence is got by 8 minus what? Group? That's very, very correct. Nitrogen has a valence of what? See?
Valence of 3.
Yeah, that's very correct. Now, are you seeing that there is a connection between your valence and the charge? Because the charge will be n to power minus 3. See? Now that one is throwing me, see?
About metalloids.
Metalloids, see? See? Now, listen. Metalloids is a group 4. Clear? Now look here. Now if you are a two-way person, who are you? Because they are in the middle. They have properties of metals as well as they behave sometimes like non-metals. See? That means they can do both. their valence would be direct, because even if you say, if you take 4, it will be 4. If you say 8 minus 4, it will still be 4. So that means their valence is the group number also. Clear? Yeah, the group number. So that's right. That's right.
Is it true that the valence should not be more than 4?
Me, I'm also asking, is it true, basing on our discussion, that the valence can't be more than 4? According to you. You see, you have answered yourself. So it can't be more than. Now look here, chemical formulae is the last discussion and the equation, but now that this one and that one, chemical formulae. See, that one has some interesting work there. See. Now a chemical formula is just a representation of a compound using symbols. Is the formula that represents a compound in form of symbols. See. Like water is H2O. See. These things are very good. Now chemical formulae are written using valences. Chemical formulae are written using valences. Then valences are categorized as valence of elements. See, and valence of now we are seeing valence of elements. Then we have something here. We are going now to, you see, we are going to introduce another language called radical. Now we saw an ion is any charged atom. Any atom having either positive or negative is called the ion. Not so? And we saw that an ion is formed by either losing or gaining electrons. So. Now we are going to see another thing called from right away we have seen atoms, molecules, ions, compounds, elements, now radicals. Yeah. Now we can just have a table of common valences that but I'm very convinced that you can now trace valences, not so? Element, I hope now I will not be speaking to myself, not so? Those with the valence 1, that means if I ask you the valence of boron, you can count your first 20 elements, you locate, then write configuration, then from configuration you pick valency. Now those that have a valence, if I wrote this, you understand now, not so? Yeah. Sodium, maybe we can write for you full. For the meantime, sodium is Na, potassium, okay, hydrogen, lithium, not so?
Hydrogen is H.
Hydrogen is H, yeah, H. Lithium is Li, not so? Yeah. Those have a valence of 1. Let me add there one called ammonium. That is, I'll bring it in radicals to carry meaning in radicals. Okay. Now here silver is Hg. Some you will see them there, you have a periodic table there. I think you were asking what is barium. Your barium is there in group 2. See?
Gold.
Gold. That's exactly. See? Now, valence 2, we have calcium, Ca, magnesium, beryllium. Now I'm trying to keep time because time has already gone. Barium. Now I'll add some more, like zinc. Some elements now will have more than one valence, as we shall see. There you are. These ones have what? 2. Those that have 3, nitrogen, boron also, aluminium. Yeah, these are 3. Now I'm going to valence of radicals that will throw us very, very fast. Phosphorus is also there. Now, valence, finished elements of radicals. Now a radical, see, listen, yesterday we talked about something in our alkalis. We mentioned the compounds like sodium. Listen attentively. I've reduced the speed there to explain what we mean by a radical. So, now, listen. A compound is listen. A compound is made. It contains more than one element, not so, because a compound is formed when 2 or more elements combine chemically, not so. Now this compound here has sodium, and yesterday we saw that hydroxide is OH, sodium is Na. Clear? Now listen, Pernicious, are we together here? Hydroxide, we cannot have an element called hydroxide. Have we ever heard of that? An element called chloride? But we can have chlorine. Now these other groups of atoms that can be attached to any element are what we are calling radicals. A radical is a group of atoms which cannot exist on their own but must exist in compound form. See? That you cannot have a chloride in the lab, but you can have sodium chloride. That means chloride can't exist alone. A radical is an atom or a group of atoms which cannot exist on its own but in a compound form. Okay. Then let us give some radicals with their valences here to assist us in writing chemical formulae. We have hydroxide, which is OH. I don't know whether somebody recall that one in bases. Chloride is Cl. Yeah, chloride, hydroxide. You know, called carbonate. Yeah, that one has a valence of 2. Yeah, bromide, C.
Sulfate.
Sulfate also valence of 2.
Nitrate.
Manganate. All have valence 1. So there is what we call hydrogen carbonate. Now when we say hydrogen carbonate, it is read as a whole thing. Don't read and say hydrogen alone, then it's carbonate alone, no? Now that is for valence 1. Then valence 2, you have told me it is carbonate. Sulfate. Carbonate, sulfate. There you are. Ammonium. Oh, ammonium, we left it here, sorry. Don't forget our ammonium is NH4, is also valence among the valences of 1. Do you see sulfite is yeah. Peroxide is O2. Then we try to, we just give a few, you'll add more from the textbooks and Google. Phosphate is PO4. This is 3. Nitride, that's also 3. Now we can end there with those valences that will help us write the chemical formula. Now, you see a radical can have a similar symbol with its element. But because an element occurs when it has not combined with anything. But when the element combines with something, you can't again call it chlorine. It's now called sodium chloride. It's now in a combined form called a radical. It changes from being an element to being called a radical. That's why you are seeing the nitride is N. That means you cannot have a nitride as an element. When you have an element, it will be called nitrogen. But then when you have a compound to call it calcium nitride, it will be now a radical because it will have been in combined form as a compound. Could we now write some formulas? Yes, now how do we write chemical formulas here? That's now examples, write chemical formulas. Write chemical formulas of each compound. That means I have like sodium hydroxide, calcium oxide, yes, magnesium, hydroxide. Now, upon me writing that, I'll also ask you to write some, then we shall look for closing the lesson. Yeah, time has yet gone. Let us try to close from there, from chemical formulas. Yeah. Now we are going to explain steps as we try to write. That when you are writing the chemical formula, you first write the symbols of the element and its radical. The symbol for sodium is Na. Clear? Yeah, sodium is Na, not so? Hydroxide, we have seen it is OH. Put a small space there. Then put their valences on their top right. Valence of sodium is, valence of hydroxide is, exchange the valences. This gives it to the other one, this gives it to the other one. Then the formula will become sodium, because one of anything is the same thing. It remains. Now magnesium hydroxide here, valence of magnesium is what? 2. Hydroxide 1. You give it, then this one also gives. Clear? Then it will become, now since these are two atoms of hydroxide, you have to put brackets. The valence is being given to both of them. Therefore you will open brackets. When there are more than one atom, you open the brackets. Here you couldn't open because one cannot affect anything. Yeah. Calcium Ca. Oxide, you see, now I think you're seeing oxygen and oxide is the same. But oxygen is the element and oxide is when it has formed the compound. When it has formed the compound, it's called a radical. Valence, calcium, oxide. Now when they have a common factor, you divide first by a common factor. Therefore you will get one and the other one also. The formula will just remain, not so? Yeah. Sodium is Na, not so? Peroxide is? It's like O2, not so? Yes. Valence of sodium? It's 1. Peroxide? 2. Here there is no common factor. Therefore these two will come here. And this one will go down, but 1 is 1. Not so? 1 does not affect anything. Therefore, you remain with Na2O2. Why do you think we don't cancel those 2's?
Because they are still.
Are you sure? Because they are? Very, very sure? So that was the suggestion. Let us compare his with hers. Yes?
I think why we don't cancel is because that it becomes the number of atoms.
This 2 is not a valence, this one. But well, this was the one. And that's why you don't cancel them. Okay. I want you to read for me this one. Sodium hydrogen carbonate. and you get for me that formula, then I see where to add calcium sulfate. We shall calcium sulfate, then yeah, and that will be the end for that under chemical formula. We shall add more on when we have introduced reactivity in the next topic. We shall do more examples and add some things on equations. Yeah. Let me hear the answers here now. Chirabo, NaHCO3. Here, patience, CaSO4. Chirabo, you are here. Mg. HCO. 3. Not really. Not really.
I think it is Mg. HCO3. You put that HCO3
in brackets.
Then 2.
Very good. Yeah. That's the end of our discussion for today. Under that topic of the periodic table, I want to read for you the activity of integration. More radicals, I'll refer you to Google and the textbook. I've given you more radicals with their valences, because I've written a few. There are some like nitrates I've not added there. Nitrates, many of them, valence of some other elements we have not added there. Yes.
How about equations?
Equations, we shall see it in reactivity. I'll handle it there before you open reactivity. Now, write this activity of integration. Are we there on activity? Yes, right. You have learnt about the role of Mendeleev. You have learnt about the role of Mendeleev. You know what he did in the development of the periodic table. In the development of the periodic table, you have also learnt about arrangement of elements in the periodic table. You have also learnt about arrangement of elements in the periodic table. And are excited about the atom. And are excited about the atom, and are excited about the atom, diversity of elements, and the entire topic. Diversity of elements and the entire topic. Imagine you were living at the time of Mendeleev. Imagine you were living at the time of Mendeleev. And you were interested in informing people about a talk, and you're interested in informing people about a talk to be given by the great scientist. Design a poster to advertise for a talk to be given by Dmitry Mendeleev. Design a poster to advertise for a talk to be given by Dmitry Mendeleev about his new periodic table. In your poster, describe these ideas clearly and state why they are important. Yeah, we shall give even more exercise, but for the interest of time, let us stop there. Now we went through the periodic table, and we said indeed it has more than 100 elements, but more are still under discovery. We arranged the elements: metals, non-metals, semi-metals. We tried to look at some of their characteristics, but metals are totally different from non-metals. And at this same juncture, I will ask you to go and list the differences between metals and non-metals. You describe that in your research work. One conducts electricity, one does not conduct electricity. I will ask you to do that in the research work. Then it took us to atomic structure, and we drilled many things: valency, the symbol, the ions, and so many things, until we landed in the chemical formulae. Now, the part of equations, we shall discuss it in the next chapter called reactivity series, before we usher in the topic. Thank you for attending.